Hello, hello everyone. My name is Zakaru Fardo, and I'm here to discuss what is nuclear power plants. Now let's begin. What is a nuclear power station? The nuclear power station is the breeding ground of civil nuclear power across the world. According to the World Nuclear Association, nuclear power forms at about 11% of the world's electricity, with 450 reactors providing 424 gigawatts of power, making it the second largest source of low carbon power in the world. So, which means nga to nga nuclear power station, mina siya ang ikaduwa nga ikaduwa sa pinakadako nga naga supplier sang electricity nga gagamit sang low carbon. Kag siya ang naga-made up sang 11% nga power or electricity nga ginagamit naton sa bilog nga kalibutan. Now, let's move on to kung paano siya mag-produce electricity. A nuclear reactor produces electricity. A nuclear power reactor produces and controls the release of energy from splitting the atoms of certain elements. In a nuclear power reactor, the energy released is used as heat to make steam to generate electricity. The principles for using nuclear power to produce electricity are the same for most types of reactor. The energy released from continuous fission of the atoms or the fuel is harnessed as heat in either a gas or water and is used to produce steam. The steam is used to drive the turbines which produce electricity, or as in most fossil fuel plants. The world's first nuclear reactors operated naturally in a uranium deposit about 2 billion years ago. These were rich in uranium ore bodies and moderated by percolating rainwater. The 17 known at Oklo in West Africa, each less than 100 kilowatts thermal, together consumed about 6 tons of uranium. It is assumed that these were not unique worldwide. Today, reactors derived from designs originally developed for propelling submarines and large naval ships generate about 85% of the world's nuclear electricity. The main design is the pressurized water reactor or the PWR, which has water at over 300 degrees Celsius under pressure in its primary cooling or heat transfer circuit, and it generates steam in a secondary unit. The less numerous boiling water reactor or BWR makes steam in the primary coolant in the primary circuit above the reactor core. At similar temperatures and pressure, both types use water as both coolant and moderator to slow neutrons. Since water normally boils at 100 degrees Celsius, they have robust steel pressure vessels or tubes to enable the higher operating temperature. Or in another type uses heavy water with deuterium atoms as moderators. Hence, the term light water and heavy water is used to differentiate the, the components of a nuclear reactor. For we have several components of nuclear reactors, but let's start with the most common or the most used component we have is the fuel. Uranium is the basic fuel. Usually pellets of uranium oxide or UO2 are arranged in tubes to form fuel rods. The rods are arranged into fuel assemble in the reactor core. In a 1000 MWE class PWR, there might be 51,000 fuel rods with over 18 million pellets. So, ang fuel naton, balaan naman natin kung anong gamit sa fuel, di ba? Muna siya nagapagana sang aton nga device, etc. kung ano man da. Sa case sang aton nga nuclear reactor, ang ginagamit ta is uranium. Ang uranium ginaano ta siya, painitan, then ang iya mga atoms naga-fission sa iban nga atoms which creates energy nga naga-make yun sang steam. Ang steam nga ina muna siya mag-propel sang aton nga propeller, like para sa principle sang dynamo, para abe maginit na siya, di ba may gagawa nga steam. Once i-contain mo na ang steam nga kita mo na daw may power na sa yun nga may pressure. Muna siyang pressure, muna siyang steam maigo sa aton nga propeller, then ang propeller matiog na tapos ang sa propeller nag-generate na siya din sang electricity naton. Then we have is the moderator material in the core which slows down the neutrons released from fission so that they can cause more fission. It is usually water but maybe heavy water or graphite. Moderator naton also known as water kay mostly ginagamit is water gid man. Since taas iya nga iya boiling point kay 100 degree Celsius ang aton boiling point sa water. Gina-slow down niya ang aton nga ang neutrons nga naga-release ang nga na-release sa fission para mag fission naman siya liwat bali daw sa sa ginagamit naton daw bali recycle lang bala or ginagamit agad ang pwede naton nga magamit sa iya. We have next component is we have the control rods or blades. These are made with neutron absorbing material such as cadmium, hafnium, or boron, and are inserted or withdrawn from the core to control the rate of reactors or to halt it in some PWR reactors. Special control rods are used to enable the core to sustain a low level of power efficiently, or secondary control systems involve other neutrons absorbers, usually boron in the coolant. Its concentration can be adjusted over time as the fuel burns up, or PWR control rods are inserted from the top. BWR cruciform blades from the bottom to the core. Control rods naton kag blades bali nagavary ang paggamit sa iya depende sa klase sang reactor nga ginagamit ta. PWR or BWR. So PWR naton ang control rods naton ginagamit naton ina-insert naton siya sa top sang aton nga reactor. Tapos sa aton nga BWR sa bottom sang core naton. So ilap ginkalain sang aton nga reactor ang paggamit sang paggamit sang control rods sa sari-sari nga reactors. Next component is we have the coolant. Coolant is a fluid circulating through the core so as to transfer the heat from it. In light water reactors, the water moderator functions also as primary coolant. Except in BWR, there is a secondary coolant circuit where the water becomes steam. So, ang aton coolant ginagamit ta primary water man Japon like moderator naton waterman, coolant naton waterman kay taas siya boiling point unlike sa uranium sa fuel naton manubo iya nga boiling point. We have the next component is we have the pressure vessel or pressure tubes. Usually a robust steel vessel containing the reactor and moderator or coolant, but it may be a series of tubes holding the fuel and conveying the coolant through the surrounding moderator. Pressure vessel naton iya function is tubes muna siya ang contain sang aton nga steam bala sa sulod ang pressure sang aton nga steam kag muna siya ang daw pathway sang aton nga steam kung diin siya magdiretso. We have the steam generator, part of the cooling system of pressurized water reactors, PWR and PHWR, where the high pressure primary coolant bringing that heat from the reactor is used to make steam for the turbine. In a secondary circuit, essentially a heat exchanger like a motor or carburetor. So balis silingon sang aton nga steam generator para sa motor daw aton nga carb naton or radiator gali naton. Mina siya ang like iya bala function sang aton nga steam generator. Now next we have is the containment. The The structure around the reactors and associated steam generators, which is designated to protect it from outside intrusion and to protect those outside from the effects of radiation in case of any serious malfunction inside. It is typically a meter-thick concrete and steel structure. And some other reactors install core melt localization devices or core catchers under the pressure vessel to catch any melted core material. In the event of a major accident, there are several types of reactor as indicated in the following table. Now, let's discuss how to fuel nuclear reactors. Most reactor needs to be shut down for refueling so that the reactor vessel can be opened up. In this case, refueling is at intervals of 12, 18, or 24 months. When a quarter to a third of the fuel assembles are replaced with fresh ones, the CANDO or CANDO and RBMK types have pressure tubes or rather than a pressure vessel enclosing the reactor core and can be refueled under load by disconnecting individual pressure tubes. The IGR is also designated for fueling on load. If graphite or heavy water is used as moderator, it is impossible to run a power reactor on natural instead of enriched uranium. Natural uranium has the same elemental composition as when it was mined from 0.7% U over 235 over 9 to over 99.2% into U 238. Or enriched uranium has had the proportion of the fissile isotope or U235 increased by a process called enrichment, commonly to a 3.5 or 5%. In this case, the moderator can be ordinary water, and such reactors are collectively called water reactors because the light water absorbs neutrons as well as slowing them. It is less efficient as the moderator than heavy water or graphite. Some new small reactor design require high assay, low enriched uranium fuel, enriched to near 20% with U-235 during operation. Some of the U-238 is changed to plutonium, and Pu-239 ends up providing about one-third of the energy from the fuel. Now let's move on to how nuclear energy is made. Nuclear plants are different to energy plants such as coal and natural gas. Despite being a thermal generation process, they do not need to burn anything to create steam. In a nuclear power plant, uranium atoms are split in a process called fission, which requires low enriched uranium fuel. Uranium fuel is formed into pellets, one of which can produce as much energy as 1 ton of coal, 3 barrels of oil, or 17,000 cubic feet of natural gas. These pellets are generally stacked into 12-foot metal fuel rods, which are grouped together in bundles that are called fuel assemblies. Thanks to nuclear fission, heat and neutrons are released from uranium. As the atoms split, the neutron hit other uranium atoms, causing them to split. Continuing the cycle, meanwhile, the released heat causes water within the reactor to boil, which in turn creates the steam that powers the turbine, which powers the generators to make electricity. So, dapat nauna tani siya discuss pero i-discuss naman siya. Ang aton nga nuclear energy nagamit, ang aton ginagamit ang product sang uranium nga atoms nga gabunggo sa another uranium atom is called fission. Though but silingon, since nagabunggo siya, ang water nga ara sa sulod niya or aton nga coolant nagainit. Hence, naga-create sang steam which mas mainit, mas grabe ang steam. Then, naga-create siya din sang ginapropel yun niya sang steam naton ang aton nga turbine. Daw same principle man Japon sa dynamo pero baliktad lang. Now let's discuss the types of our nuclear reactors. There are two standard type of nuclear reactors. Firstly, boiling water reactors or BWR, which simply heat up water until it boils to spin turbines and generate electricity. Secondly, pressurized water reactors or PWR, which heat up water to close to boiling point before this water is pumped into a separate supply of water. In this compartment, it becomes steam that is used to power a turbine. So, most damo kita power reactors pero ang duwa ka bilog. Bali ang una is ang aton boiling water reactors nga simple lang iya nga design. Then ang aton nga PWR or pressurized water reactors. Let's discuss what is boiling water reactor. This type of reactor has many similarities to the PWR, except that there is only a single circuit in which the water is at lower pressure or about 75 times at atmospheric pressure so that it boils in the core at about 285 degrees Celsius. The reactor is designed to operate within 12 to 15% of the water in the top part of the core as steam, and hence this with less moderating effect and thus efficiency there. BWR units can operate in load following mode more readily than PWRs. The steam passes through dryer plates, steam separators above the core, and then directly to the turbines, which are thus part of the reactor circuit. Since the water around the core of a reactor is always contaminated with traces of radionuclides, it means that the turbine must be shielded and radiological protection provided during maintenance. The cost of this tends to balance the savings due to the simpler design. Most of the radioactivity in the water is very short-lived, so the turbine hull can be entered soon after the reactor is shut down. A BWR fuel assemble comprises 90 to 100 fuel rods, and there are up to 750 assemblies in a reactor core, holding up to 140 tons of uranium. The second control system involves restricting water flow through the core so that the more steam the top part reduces power moderation. Let's go to our another type is pressurized water reactor or PWR. This is the most common type with about 300 operable reactors for power generation and several hundred more employed for naval propulsion. The design of PWRs originated as a submarine power plant. PWRs use ordinary water as both coolant and moderator. The design is distinguished by having a primary cooling circuit which flows through the core of the reactor under high pressure, and the secondary circuit in which steam is generated to drive the turbine. In Russia, these are known as VVER types or water moderated and cooled. A PWR has fuel assemblies of 200 to 300 rods each arranged vertically in the core, and a large reactor would have about 150 to 250 fuel assemblies with 80 to 100 tons of uranium. Water in the reactor core reaches about 325 degrees Celsius, hence it must be kept under around 150 times atmospheric pressure to prevent it boiling. Pressure is maintained by steam in a pressurizer. In the primary cooling circuit, the water is also the moderator, and if any of it turned to be the steam, the fission reaction would slow down. This negative feedback effect is one of the safety features of the type. The secondary shutdown system involves adding boron to the primary circuit. The secondary circuit is under less pressure, and the water here boils in the heat exchangers, which are thus steam generators. The steam drives the turbine to produce electricity, and it is then condensed and turned to the heat exchangers in contact with the primary circuit. Let's discuss ang ato naman nga another type of nuclear reactor, pero hindi man siya mas common Kaya atong duha mo to gid ang common naton nga makikita. Ang isa is light water graphite moderated reactor or LWGR. The main LWGR design is the RBMK, a Soviet design developed from plutonium production reactors. It employs long 7-meter vertical pressure tubes running through graphite moderator and is cooled by water, which is allowed to boil in the core at 290 degrees Celsius and at about 6.9 MPa, much as in the BWR. Fuel is low enriched uranium oxide made up into fuel assemblies 3.5 meters long. With moderation, largely due to the fixed graphite, excess boiling simply reduces the cooling and neutron absorption without inhibiting the fission reaction, and a positive feedback problem can arise, which is why they have never been built outside the Soviet Union. Which now may isa pa kita ka reactor is a fast neutron reactor or the FNR. Some reactors do not have a moderator and utilize fast neutrons generating power from plutonium while making more of it from U-238 isotope in or around the fuel. While they get more than 60 times as much energy from the original uranium compared with normal reactors, they are expensive to build. Further development of them is likely in the next decade, and the main design expected to be built in 2 decades are FNRs. If they are configured to produce more fissile material or plutonium than they consume, they are called fast breeder reactors or FBR. Let's go to our advanced reactors. Several generation of reactors are commonly distinguished. Generation I reactors were developed in the 1950s and to 60s, and the last one shut down at the end of 2015. They mostly use natural uranium fuel and use graphite as moderator. Generation 2 reactors are typified by the present US fleet and most in operation elsewhere. They typically use water-enriched uranium fuel and are mostly cooled and moderated by water. Generation 3 are the advanced reactor evolved from these, the first few of which are in operation in Japan and from early 2018 in China, Russia, and the UAE. Others are under construction from these, the first few of which are in operation in Japan and from early 2018 in China. Safe. There is no clear distinction between Generation 2 and Generation 3. Now, but we have Generation 4 designs are still on the drawing board. They will tend to have closed fuel cycles and burn the long-lived actinides now forming part of spent fuel. So that fission products are the only high-level ways of 7 designs under development with international collaboration. 4 or 5 will fast neutron reactors. 4 will use fluoride or liquid metal coolants, hence operate at low pressure. 2 will be gas cooled by most run at much higher temperature than today's water-cooled reactors. So that were the advanced reactors. Now let's go to floating nuclear power reactors. Apart from 200 nuclear power reactors powering various kinds of ships, Rosatom in Russia has set up a subsidiary to supply floating nuclear power plants ranging in size from 70 to 600 MWA. This will be mounted in pairs on a large barge, which will permanently moored where it is needed to supply power and possibly some desalination to assure settlement and industrial complex. The FIR has 240 MWE reactors based on those in icebreaker and operates at a remote site in Siberia. Electricity cost is expensive to be much lower than the present alternatives. alternatives. So that is another type of our nuclear reactors. We have another react in another type. Pila ni? Bale may tatlo pagid ta ka type nga nuclear be last naton nga power rating, last type of reactor naton is the power rating of a nuclear reactor. Moto na siya gali ang last type naton, ang floating nuclear power plants. Now we discuss the power rating of nuclear reactor naton. Nuclear plants reactor power outputs are quoted in three ways. Thermal MWT, which depends on the design of the actual nuclear reactor itself and relates to the quantity and quality of the steam it produces. Gross electrical MWE, which indicates the power produced by the attached steam turbine and generator, and also takes into account the ambient temperature for the condenser circuit, or the cooler means more electric power, warmer means less. Rated gross power assumes certain conditions with both net electrical MWA, which is the power available to be sent out from the plant to the grid after deducting the electrical power needed to run the reactor or the cooling and feed water pumps, etc., and the rest of the plant. Now, let's discuss the lifetime of nuclear reactors. Most of today's nuclear plants, which were originally designed for 30 to 40 years operating lives, however, with major investments in system, structures, and components, operating lifetimes can be extended. And in several countries, there are active programs to extend operation. In the USA, nearly all of the almost 100 reactors have been granted operating license extension from 40 to 60 years. This justifies significant capital expenditure in upgrading systems and components, including building extra performance margins. Some will operate for 80 years or more. So, but siningon sa aton nga ang lifetime sa aton nuclear reactors is mostly is 30 to 40 years lang ang ginahatag sa ila. Pero since muna lang daw para sa aton daw kadasig lang. So why ma-waste kita sang kwarta nga dira kag maobra naman sa bag-o. Not only we spend money, spend pagita sang time kag ang space nga gamito naton daw kanugon man daw waste na lang. So, mas med na ma-invest kita para ma-extend ta ang lifetime sa aton nga mga reactors, since daw makas other than money, makas-save kita sang space mambala, daw less pollution man gyapon ang gwa niya kung sige-sige ta lang siya nga gamit. So let's discuss ang aton nga primary coolants. First is we have the water or heavy water. It must be maintained at high pressure with 1000 to 2200 psi or 1715 MPa or 150 atmospheres to enable it to function well above 100 degrees Celsius or up to 345 degrees Celsius. As in present reactors, this has the major influence on reactor engineering. However, supercritical water around 25 MPa can give 45% thermal efficiency, as of some fossil fuel power plants today with outlet temperature of 600 degrees Celsius and at ultra supercritical levels of 30 MPa, 30 plus MPa or 50% may be attained. Now we have another coolant is ang aton helium. Helium must be used at similar pressures, 1000 to 2000 psi or 7 to 14 MPa to maintain sufficient density for efficient operation. However, even at 75 atm pressure, its heat capacity is only about 20 kilojoule meter per cube. Again, there are engineering implications from the high pressure required, but it can be used in the Brayton cycle to drive a turbine directly. We have the carbon dioxide. It was used in early British reactors and their current AGRs, which operate at much higher temperature than light water reactors. It is denser than helium and thus likely to give better thermal conversion efficiency. It also leaks less readily than helium. There is now interest in supercritical CO2 for the Brayton cycle. So those are coolants, and next we have sodium. Sodium have lead or lead bismuth eutectic, and next the salt or the fluoride salts and the chloride salts, and all low pressure liquid coolants. Muna lang sila itong mga coolants nga ginagamit, pero mostly gid ang ginagamit is water gid, kay muna gid siya ang pinaka basic nga kang pinaka nami labi sa reactors ng ianda naton sa devices. Now we have the load following capability sa ating power plant. Now let's discuss the load following capability of our nuclear reactors, nuclear power plants. Nuclear power plants are best run continuously at high capacity to meet base load demand in a grid system. If their power output is ramped up and down on a daily and weekly basis, the efficiency is compromised, and in this respect they are similar to most coal-fired plants. However, in some situations, it is necessary to vary the output according to daily and weekly load cycles on a regular basis. For instance, in France, where there is a very high reliance on nuclear power, Areva has developed its advanced load following control system for PWRs that automatically adjust the plant's electrical output according to the needs of the grid operator. It involves a software upgrade of the reactor control system which varies the plant output between 50% and 100% of its installed capacity without intervening of the operator. So, buds lingon ang aton nga ang load sang aton nga nuclear power plants naga-depende man best gid nga ang iya load nagagana gid siya continuously sa the same capacity sang aton nga system. Kay once nga siya, hindi siya mag continuously nabla nang hindi siya stable ng aton ang iyang efficiency samad man. That's why nga dapat stable gid siya para same man gyapon iya pag-produce ang electricity, same wala naga-fluctuate ang electricity naton. Now let's discuss how nuclear reactors process heat. Producing steam to drive a turbine and generator is relatively easy, and a light water reactor running at 350 degrees Celsius does this readily. As the above section and figure show, other types of reactor are required at higher temperatures. A 2010 US Department of Energy document quotes 500 degrees Celsius for a liquid metal cooled reactor or FNR or 860 degrees Celsius for a molten salt reactor or MSR, and 950 degrees Celsius for a high temperature gas cooled heater or HTR. Lower temperature reactors can be used with supplemental gas heating to reach higher temperature, though employing an LWR would not be practical or economic. The DOS said that the high reactor outlet temperatures in the range 750 to 950 degrees Celsius were required to satisfy all end user requirements evaluated to date for the next generation power plant. So, now let's go sa aton nga mga primitive reactors. The world's oldest known nuclear reactors operated at what is now Oklo in Gabon, West Africa, about 2 billion years ago. Wow, dugay-dugay. At least 60 natural nuclear reactors achieved criticality in a high-grade deposit of uranium, or A-17 was in the Bagombe deposit 30 km away. Each operated intermittently that at about 20 kilowatt thermal. The reaction ceasing whenever the water turned to steam so that it ceased to function as moderator. At that time, the concentration of U-235 in all natural uranium was about 3.6 instead of 0.7 as at present. U-235 decays much faster than U-238. Those were isotopes, sa mga U, whose half-life is about the same as the age of Earth. When the Earth was formed, U-235 was about 30% of uranium. This natural chain reaction started spontaneously and continued for overall for about 1 or 2 million years before finally dying away. So, ang example sa aton nga primitive reactors ang aton mga volcano. Depende kung di na nga klase nga volcano para sa Pilipinas Taal Lake dabi naton, which is ara sa ilog, which is those sa lawa or closed space nga daluyan sa tubig, which is nga ang sa tunga. So ang yang ginagamit dira nga coolant is ang aton nga ang water, ang gapalibot siya nga tubig. Then ang iya heat or iya steam, iya heat nakalin gid sa dalom sang duta, which is ang aton nga earth nga made up of magma. Then nagagawa siya sa aton nga volcano. Then and water, ang aton nga water naga create siya sang steam, which kung enough na ang steam nagaalsa ang aton nga volcano, ang magma sang volcano naton, which naga-cause ng eruption. Though the same principle sang aton nga ginagamit, since ang volcano may pathway na siya halin sa core mo pababaw, muna siyang aton nga tube, ang aton high pressure tubes or control tubes or rods or blades naton, which is ginapaagay niya dira ang nagtipon nga pressure sa dalom sa magma nga pagwa sa iya ginalupok. Now we have here the figure of our BWR and our PWR na na aton nga nuclear power reactor. Kung makita nyo dire sa BWR naton, ari dire ang iya reactor, siya ang reactor vessels naton. Once aring mga control rods naton, aring mga pathways, once nga mag-steam na siya diretso na siya dire, tapos aton nga turbine malibot na ang turbine, which then sang generator, then i-output is electricity, where there is a condenser naton, ang magsobra dire na turbine magwa siya dire condenser na dire naman siya libot-libot lang, balik naman diyan kung pwede. Sa aton nga PWR, though the same man lang siya gapon nga pero though nagdamo lang nagdamo lang yung mga parts. Alin dire sa pressurized, though ginapataas niya ang pressure naton, then diretso di sa steam turbine condenser naman diyon. Mas may mga feed water pump pa siya para hindi siya mag-init, masubrahan sang init, since nga may pressurized na sa kadaan. Then aton generator is electricity naman diyon, balik-balik lang. Now let's discuss the pros and cons of our nuclear power. As nuclear power does not need to burn anything to create a steam, it does not emit greenhouse gases like methane or CO2, which is makabulig sa aton nga natural sa pollution problems naton. Once a nuclear plant is up and running, the electricity it produces is inexpensive due to the low cost of uranium. Unlike wind and solar, nuclear is a consistent, reliable source of energy which can run uninterrupted for up to a year. So, muna siyang pros sang aton nga nuclear power. Unlike wind kag sa solar or any panada nga water nga ginagakuan ta sang electricity, ang aton yang nuclear is very consistent, which is reliable source gid sa sang aton nga energy. Unlike sa solar, mula adlaw, gaulan, wala siya solar, wala power, which is wind, wala hangin, wala gatiog ng turbine, wala hangin. Amo man na sa iban kung wala ilangan natural ginagamitan nga natural, wala siya. Tapos ang aton nga wala siya naga-release sang greenhouse gases para sang methane or CO2 kay natural lang siya. And ang aton once magamit na ang nuclear plant nga diretso na sa ang aton electricity, hindi siya mahal kay barato ang uranium naton kay damo uranium. However, the initial cost of building a nuclear plant is steep. A recent versatile test reactor or VTR project in Idaho is estimated to initially cost between 3.9 and 6 BN and 550 to 850 million every year for 7 years. This is much more than the initial 3 billion estimate given by dollars by Idaho National Laboratory head Kemal Pasame Tuglu. While the running costs over 7 years is more than 219 budget for the Department of Energy entire nuclear technology development program, which sits at 740 million. A similar story is true around the world, which reactors often coming in over budget and delayed. So ang aton nga cons mo ni siya, ang aton nga ang pag-build naton sang nuclear power reactors kay mahal gid siya masyado. O wala problem sa fuel, wala problem sa iya consistency, pero ang cost nga mag-build ka sang isa kag mag-maintain ka sang isa is mahal, which wala budget ang wala may ara man budget pero hindi siya makaka-supply always ng budget sa aton nga mga power reactors. Nuclear plants, like all thermal generation, produce waste. However, unlike other waste streams as it is radioactive, but 97% of the waste produced is considered low or intermediate level waste, and as such is easily disposed of. The nuclear industry produces 30,400 meter cube of high level waste globally a year. But counter to what many people believe, it does not take forever to degrade. It is generally stored in the interim storage where within just for 40 years, its radioactivity level decreased to 1,000 of the level. So, muna naman ang aton nga pros. Ang aton nga advantage sa nuclear power plants. Ang iya nga, 97% sang iya nga waste is only considered low or intermediate level lang. So, hindi siya parehas sang any other nga plants nga ang iya waste is siya dumal. Oo, delikado gid man siya since nuclear. Pero within 40 years, ang radioactivity sang aton nga nuclear power plants nagaanubo or ang iya waste nagaanubo sa 1,000 of the level nga from 1,000 to 1. So, betlingon lupos siya i-dispose. Finally, the potential for disasters such as Chernobyl and Fukushima is a concern when considering nuclear power. Both had devastating effects upon their environment and the community close by. However, it's to remember that together with 3 Mile Island, there are only major in over 17,000 cumulative reactor years of commercial nuclear power operation in 33 countries. So, bisan i-consider to siya nga sobra gid man kadelikado ang aton nga power reactor, pero nagadelikado lang siya para sinang sa Chernobyl kag sa Fukushima nga nasamad siya by natural calamity, and tuod sobra gid man niya kadelikado since hindi kagid ya kapalapit sa nuclear reactors naton kay kagid mapatay kagid, or hindi ka mapatay damo masakit sa imong lawas kag sa palibot naton. Plants to animals, delikado man sila once ma-expose sa radioactivity. So, moto ng pros and cons, and that's conclude the end of my report, and thank you for listening everyone, and that is it.